again. All right, 10.8 is geometric probability. All right. Of all the probabilities that we talk about, I think geometric probability is probably the most straightforward. We don't have to do a whole lot, at least right now, in regards to like independence and dependence and all that kind of stuff that we deal with when we kind of put like marbles in a bag or names in a hat or cards in a deck or something like that, or rolling dice. We're asking maybe to, you know, what's the probability that I pull out Cameron's name, followed by Gage's name, followed by not Chandler's name. Those are maybe difficult probabilities that we got to deal with. Geometric probability is not that complex, okay? In order to talk about probability, it's probably a good idea to talk about some notation things, some definition stuff. Probability, by definition, just the likelihood of an event occurring, okay? The likelihood or the chance that something happens, okay? And we usually write that as, instead of saying, what is the likelihood that this thing happens, we just say capital P for probability, and then we put in parentheses that thing that we want to happen, okay? Or that thing that we're interested in happening, okay? So let's say that if we go back to kind of old probability examples that maybe we've done in the past, we say we put all our names in a hat, and I ask what's the probability that I pull my name out, or likelihood to pull out Mr. Fay's name, then we would write that as P parenthesis Mr. Fay, right?
Yes.
Okay. Then how do I find the numerical value for that? How would we go about doing maybe the algebra for that?
You would do like, how many kids on this house?
Let's say 20.
20, you would do like 1 out of 20. Like
Okay, so 1 out of 20, there's 20 people in here, so it'd be 1 would be the numerator being the outcome that is aligned with my event. Does that make sense? Okay, because there would be 20 outcomes, right? Could be Gage, could be Chandler, could be Janet, could be Cameron, could be Kyle. Okay, there's 20 names in there, right? So each one of those is a possible outcome, but the one that's aligned with the event probability of Mr. Fay, there's only 1 in there, okay? So the numerator becomes what we call our favorable outcome, okay? Things that are aligned with the event or match up to our event. The denominator becomes all possible things that could happen, okay? Which there's 20 names in there, so each one of those things could be a possibility. So that's how we do probability across the board, okay? Regardless of whether we're pulling names out, pulling marbles, doing probability for geometric models or whatever, it's the numerator is always your number of favorable outcomes, and your denominator is the number of possible outcomes, okay? Usually the denominator is referred to as your sample space, okay? Sample space. You guys have heard that before, right? Okay. All probabilities are going to be between 0 and 1. Okay. We can write them as fractions. We can write them as decimals. And we can also write them as percentages if we want to. However, the decimal and the percentage are directly linked, right? A lot of times as you get into further mathematics, it uses probability, like a probability in stats class. You don't usually change things to percentages. Usually on a decimal. Okay. A lot of things that you do in stats, okay, relate to probabilities, okay? You don't do this a whole lot in stats. You don't, when people think, oh, I'm going to take stats because I like baseball or I like football, and we can talk about that kind of stuff. Those are statistics that represent and explain that sport. But that's not really what you do in a stats class, okay? A stats class takes, a bunch of data. It starts providing you a way to kind of interpret that data and use that data to determine the probability of some event that is not happening yet or has not happened yet, and determine what is the likelihood that it does happen. Does that make sense? Okay. Or it allows you to do research on a particular thing, and statistics and probability that tell you, if I've done research that shows that if a student comes to school 140 days out of the school year, then they are likely a C student or something like that. If I've done research on that, probability statistics class tells me then basically how to determine how confident that statement is, okay? or how confident I am in saying that the next person that comes to school only 140 days out of 180, they're a C student. Okay, I might be 99% confident or 95% confident that that's going to be able to be tacked onto that person. Does that make sense? Okay, so those are the kinds of things you deal with in a stats class. But statistics drive the probability. Does that make sense? Okay, they allow us to develop probability. For instance, probably this last class. Let's say Gage and Abby. Let's say they had the birthday on the same exact day. Okay, they're exact same age. They go to the license bureau, get their license on the exact same day. They get a brand new car, the exact same model, the exact same color. They get it on the same day. But they go both to the insurance agent on the exact same day, the exact same time. They buy the exact same policy. Who is paying more? Gage. Why? Okay, good. So Gage is going to pay more because Gage is a 16-year-old male. Okay? And studies show, past experience shows, that 16-year-old males are a little bit more reckless, right? They don't make the best decisions, right? So they're more likely to get in an accident, right? The probability of the insurance company having to pay a claim on Gage is much higher than having to pay on Abby. Why does, some of you that might be in the situation where you're maybe helping mom and dad pay insurance or something like that, or mom says you got to get your grades up because the insurance company gives us an incentive. They give us a deduction on our policy when you have a 3.0 or something like that. Why? Why does the insurance company do that?
Because the smarter you are, the smarter you make decisions.
Okay, so they're saying that there's a link between your decisions that you make educationally and the decisions that you make behind the wheel. Okay? And if you're likely to be cautious and cognizant of your grades, then you're probably going to be cautious and cognizant of the decisions you make when you're driving. Okay? Usually 4.0 students don't go outside doing donuts in the middle of I-75, right? Okay. So those things are directly linked to probabilities. Okay?
Because girls make more severe crashes though.
If let's say we had Gage and Cameron, let's say we do the same exact thing with them, but they buy the exact same cars, same birthdays, all that kind of stuff, but Gage's car is beige and Cameron's car is bright red. Who pays a higher premium? Cameron.
Wait, what?
Okay?
He has a
Because probability shows that a red car, okay, elicits certain emotions that want or force people to want to drive faster. And if you're driving faster, you're more likely to crash. Okay? Colors elicit emotions, don't they? Okay, why are most of your go drive around? Why are most restaurants yellow and red? Because those colors make you hungry. Okay. So there's a lot of that kind of stuff kind of at play in insurance. I live across from a fire hydrant. Okay. My insurance premium is less than a house that doesn't live across from a fire hydrant that is of lesser value than my home. Does that make sense? Okay. So say my neighbor down the street has a lesser value home than me, but they don't live across from a fire hydrant. They have to pay more money to insure their house than what I do, even though my house is worth more. Does that make sense?
Yes.
Because the likelihood of the fire department putting out the fire at my house and saving my house is higher because of the access to the fire hydrant. Does that make sense? Okay. I have a diving board. My neighbor doesn't. Okay. Whose premium is higher?
Yours.
Mine. Why?
Because you're very bored.
For what?
Because they don't.
Yeah, there's more likelihood that there's going to be an accident there, right? And my homeowner insurance is going to cover me up to I think it's like $1 million on injuries that occur at my house. Does that make sense? Okay. So probability impacts you. It's very important. Okay. Now we're not going to get so much into that type of probability, like probability with insurance and stock markets and stuff like that. If you're in a stats class that is taught like a legitimate stats class, that is something that you will do. Okay. stats is one of the courses that you can make it as hard as you want to, or you can make it really, really, really simple and easy. Okay. Geometric probability. Okay. The probability we're talking about, the most part, uses geometric models to solve probability questions. Okay. And the event of doing that, the models that we're going to really use are segments in particular areas. Okay. Regions in a plane. Okay. So we're talking about, if we think about that, then segments have lengths, regions have areas, so we should be relating segments to segments and areas to areas. And then that's what geometric probability is all about. All right, so the first key concept, first type of question you get is the idea, and you might see people doing this at, you ever go through a drive-through, like a fast food drive-through, and while you're sitting waiting there, you'll see some people over in the corner, maybe in a car or outside the car, and they'll have a bunch of tablets, and it looks like they stopwatches and stuff like that. Okay, what they're doing, I've seen this happen many, many times. Like McDonald's or Burger King, or I don't know if Happy Days would do this because they're more locally owned than those other two. When you're in line for something, it's called, you're in a queue. Okay, queue is another word for a line. And McDonald's and Burger King are interested in it being fast food, right? And they want you to get there, order, and in a reasonable amount of time, get your order and leave, right? Happy Days. You ever been to Happy Days, right, Jenica?
Yeah.
You're not so concerned about me waiting, are you?
I mean,
I've been to Happy Days, and I've waited for like an hour.
because our food's fresh.
Right, okay. But they want to make sure that when you're in that line, okay, these people from McDonald's or Burger King, when you're in this queue or this line, they want to make sure that when you, at any time that you drive up, there is a probability that you get your food within some time frame. Does that make sense? And that is what this question here is kind of targeting. And there's no context to the question or example we're doing right here. I'll show you one in a moment that does have context so you can kind of relate to maybe how fast food restaurants do it. But it says point S on AD is chosen at random. So you got all these points from A to D. There's an infinite number of points on there, right? Okay. You're choosing one at random. You got your eyes closed, you put your hand on there, pick it out. We want to know what the probability was that you picked one that came from that red segment between B and C. Okay? Well, in geometric probability, what that means is that we're comparing the length of BC. The probability that S showed up on BC would be simply the length of that segment compared to the length of that segment. If we divide those distances, that will give us the exact probability of that occurring. Does that make sense? Okay. So, looking down here at this question here, it says point K is on ST. So point K is somewhere between 2 and 14, right? Okay. Including 2 and 14. It says some point is chosen at random. What is the probability that K lies on QR? So what we'd be looking at, we'd say probability that K is on QR. Okay. So that would mean that we're going to take favorable outcomes would be the outcomes that are aligned with this, right? So we're looking for the points that are on QR. Well, the points that are on QR are identified by the distance of QR, right? What's the distance of QR? 3. Distance. 1, 2, 3. No. Okay. Then I want to talk about the distance that it could have came from. So I closed my eyes and I picked a point, and I wanted to see if it was on QR, but I could have picked any one of these points, right? So what is that distance? 12. So what's 3 out of 12? 1/4, which turns into 0.25 or 25%, right? Okay. So that would be the probability that our point lies on QR. Now here's a question to you, or for you. Could I say what is the probability not on QR? What would that be? 75%. 5, right? How can you determine it? How did you decide that? Jennifer?
Because the probability of QR is 25 and of like 100%, so you just do 100% minus 25.
Good. Okay. So when I want to find the probability of not something, a lot of times what I can do is go 1 minus the probability of that something. Does that make sense? Okay. And that's actually a property that we're going to be pretty interested in, and it's called the complement. Okay. Think about complementary angles. If I tell you 20 degrees, what's the other one?
80. Wait, you said 20?
20 degrees. Complementary angles, 20 and 70, right? So we have defined in regards to complementary angles, the total should be 90, right? So if I tell you one of those angles, you should automatically tell me the other one because you know that's your total, correct? Well, if I talk about two events being complementary, one is the event that it happens, its complement is the event that it doesn't happen, right? And probability should total to 1. So that's why we take 1 minus the probability of the event, and it tells me the probability of not happening. So today's probability of rain was 30%. So what's the probability it's not going to rain? 70%. 70%. So that 70% is the complement of it raining. Okay. So a couple different notation things that we talk about for probability, and that is, or I guess not probability, but the complement of probability. All right, so probability, the way, the notation I have right here is the way we read this. The probability of an event. So probability of an event would look like this. Probability event. Okay. If I put this little parenthesis or prime notation, sometimes we call that, we read that P prime. It refers in probability as complement. Okay. So we'd be saying what's the complement of this event's probability. Another way of writing it is P and then putting a superscript, a C there, and then writing the event. Okay? So if I wrote P complement of on QR, okay, what that really means is what's the probability that it's not on QR? Does that make sense? Okay. A third way of writing it is to use capital P, and then they put a bar over the top of it. Okay, so when I write something like that, we read that P bar. Okay, but all those notations mean complement. Okay, it's just text to text. They might change back and forth. So it's just something to think about and look at as you go through. There's a branch of mathematics you guys will talk a little bit about. It's called set theory or group theory, where this notation is used again for that stuff. So that's pretty useful. Jennifer?
You said that the P on QR means that it's not on QR.
If I write it with this C or this bar here, so P prime, P, C, P bar, they all mean P not on QR if P meant on QR. It's not a huge, and we're not going to see it too much in this class. But I just wanted to provide that notation for you. If you see it through like your homework and they put like P and then either a bar or a C or a prime notation, they're meaning what is the complement. So do 1 minus whatever you found. I think that might be the safest thing right now for us to try to think about. So try to do an example here that relates to this distance concept. This says a commuter train runs every 25 minutes. Okay? It says if a commuter arrives at the station at a random time, what is the probability that the commuter will have to wait at least 10 minutes for the train? Okay? Assuming that the train stops and the time that they stop is something we're not really interested in, that's negligible. So once it shows up and stops, the timer starts over again. Does that make sense? We don't have to wait like 2 minutes and then takes off and now the 25 minutes starts or whatever. So start and go 25-minute increments. Does that make sense? Okay. So here in this number line, so what we do is we take this 25-minute increment and we make, because time can be put in that number line, right? So we put that number line out from 0 to 25. Okay. And the question says, what is the probability the commuter will have to wait at least 10 minutes? As you do probability, and this is just not GMS probability, it's all probability, there's key tag phrases that are like at least, at most, no more than, no less than, things like that that you have to understand, okay? At least would mean what? 10 minutes or more, okay? At least means that is the bare minimum that we have to wait, okay? But it could be more, all right? So what we do is say, okay, if 0, okay, the last train has left, and this right here starts the timer for the next train to show up, right? Okay. If I show up right there, do you have to wait at least 10 minutes?
Yeah.
If the train shows up at 25, and I'm right there at 22, do I have to wait at least? No, I'm waiting 3 minutes for the train to show up now, right? Okay. So if I show up right there, I still have to wait less than 10 minutes, right? So I'm not meeting that requirement of having to wait 10 minutes or more. The only places that I can show up and I have to wait 10 minutes or more, let's say I show up there. The train doesn't show up for another 20 minutes, right? Am I within waiting at least 10 minutes? Yeah. So everywhere on that little red segment A to C would be where if I show up during that time interval, I have to wait at least 10 minutes for the train to show up, correct? So the probability of me showing up then and waiting at least 10 minutes would be AC's length, which is 15, divided by AB's length, which is 25, reduced to 3/5, 60%. Okay? So there's a probability that's showing up at a random time in this event. Okay? A random time in this scenario. I'm going to have to wait 60, or I'm going to have to wait at least 10 minutes 60% of the time. Meaning that for every 10 times I go to the bus stop or the train stop, okay, 60% of those times I'm going to be waiting more than 10 minutes. Does that make sense? Okay. Now if it says what is the probability the commuter will have to wait no more than 5 minutes? No more than 5 minutes means what?
You don't have to wait more than 5 minutes.
I don't have to wait more than 5 minutes. So I'm waiting only 5 minutes, 4 minutes, 3 minutes, 2 minutes, or 1 minute, right? Or 0 minutes. Okay, so I show up and I just walk around on the train, right? Would you guys agree that that represents no more than 5 minutes? Would represent that little blue region? So would that probability be 5 over 25? Okay. So that's kind of what we go back to what I said at the beginning with McDonald's and Burger King and these queues. That's kind of what they do. Okay. They're taking data so that when you drive up, okay, at any time during the day, or maybe any time during like peak hours of operation, like breakfast, lunch, or dinner, that you're waiting no more than maybe 10 minutes. Because after that, maybe it's considered not fast food, right? Happy Days?
Okay, it's not drive.
Wait, I have a question.
It's the math word for a line.
But even though they serve you an amount of time, it's usually never right if it's within like at least 2 minutes of the huge backup.
Yeah.
It's almost never right in McDonald's.
All right. I think you spell Q like Q U
Wrong chicken?
U E.
What do you get from Happy Days? What do you get from Happy Days that takes so long?
Probably-
Everything. Whatever you get there takes forever.
Probably-
Okay, I'm not saying it's bad food.
Bad food. Only a 3-course meal with dessert included.
I do like the Cadillac.
Ew, that is the most disgusting thing ever. It's literally
It's
like
like-
ice cream.
It's like ice cream
32 ounce cup. Listen to this.
on steroids in heaven.
Brownie, whole banana, 2 cups of M&M's, chocolate syrup, more ice cream. It's got something else.
It's like a heart attack with 2 spoons. It's pretty good.
And it is whipped cream, Oreos, and carrots.
Yeah,
It's supposed to be
it's really good.
It's really good. I mean, I can eat all of them.
They give you 2 spoons because you're supposed to eat with somebody else. Oh, what did I do that?
Just use two.
I see it twice as fast.
I could eat anything else but the one thing that's in there, like actually brownie, I think it was.
All right, so we got that line segment concept, okay, but we also have the ability to deal with areas, okay, and this more of your questions kind of align with this. The idea, I always kind of relate the idea to throwing darts, okay? And being really bad at darts, having no skill. Because sometimes, in regards to having a skill, can make your events maybe less likely to occur. Does that make sense? Or not equal to occur. If I'm really good at darts, it's probably, and I'm trying to hit that yellow up there in that key concept block, in that triangle region, and I'm good at darts, there's something that's skewing the probability that I hit that yellow than I hit the blue, right? Okay? Think about this, the probability that a major league hitter goes up and hits a 99-mile-an-hour fastball is a lot more higher than the probability that I go up and hit that, right? Okay? So, when we look at areas, I'm going to kind of talk about, throwing a dart or something like that, or picking a point out at random with your eyes closed, some type of concept like that, because that provides these points to be equally likely to occur. But all it is the same concept as what distance was. Distance was favorable outcomes divided by total outcomes, right? Well, if my favorable outcome is to land in that, or to land a dart in that yellow triangle, or to pull a point out of that yellow triangle, then these points in this yellow triangle, all of them are being represented by that triangle's area, right? Okay. And then all possible outcomes in my sample space would be everything in that overall quadrilateral, okay, which the yellow is part of. Does that make sense? Okay. Now, some people say, well, what if I don't even throw the dart and hit that? Well, that's something we got to think about here. Okay. A lot of times we're thinking about, this. Maybe we'll look at this example down here. Okay. Maybe I got to add in the fact that you're going to hit the board. Okay. Because then there is probably, yes, I could hit out here. I could not hit that. So we maybe have to take that into account. Maybe some higher level math would maybe be involved. Okay. So let's take that example down at the bottom. It says a circle is inscribed in a square. Point Q is picked at random. What's probability Q lies in the shaded region? Okay. So Q could maybe be that point there, or maybe that point there. What is the probability of landing in any of these points or positions? So we got to find these respective areas. Does that make sense? We got to find the area of the shaded region. Well, the area of the shaded region, and this is why we've given this point or this question several times in homework, does it have a really nice formula? Do you have a name for that little region right there? No, so you probably don't have a formula for it. So, in the past, we've been taking area of the square and removing from that the area of the circle. Would that give you the area of the shaded? So what's the area of the square going to be? 36. Okay. What's the area of the circle going to be? Now think about it. What would that distance right there be? 3. So my area of my circle would be pi r squared, or 9 pi, right? So the shaded region, what would I do with these two numbers to get my shaded region? Okay, so you have 36 minus 9 pi, right? So that would be all these shaded regions. Okay. What is the total target area? That would have been the square, correct? So I put the squares area on the bottom. And I could evaluate that. Okay, grab my calculator. Gives me that number right there, right? Okay, 36 minus 9 pi over 36 is 0.21. So 21.4% chance that I hit those yellow regions, right? What's the probability that I don't land in the shaded? Okay, this is the way maybe we could write this. Okay, let's just say that this probability here, probability that Q lies in shaded region, we just said that was 0.21, right? What if I say probability, maybe I put this notation, maybe I put that notation, or maybe I put the bar, okay? And then I say Q lies in the shaded. That would equal the complement idea, right? Complement is the probability that it happened removed from 1. And if I do that, it gives me about 0.79. Does that make sense? So probability of landing in here. So another way I could write this, maybe a more friendly way of writing it, probability, or the complement probability of lying in the shaded region would be the probability of landing in the white, correct? Or maybe you would write it the probability of landing not in the shaded region, okay? So those are all kind of different ways that we can verbalize what we mean by landing in the white region, okay? But they should total to what? It should total to 100%, okay? So a lot of questions are very similar to that. I want to do at least one more with geometric probability. And it's this. It's a very common question. You see it several times in your homework. We got a bunch of concentric circles. We talked about concentric circles the other day. Here it says an archery target has 5 colored scoring zones formed by concentric circles. The inner circle, the yellow, has a radius of 12.2. The diameter of the whole target is 122. We want to know what's the probability that a randomly shot arrow hits the red. Okay? So we've got to kind of figure this stuff out. And it also says that the width of every other region is 12.2 centimeters. Okay? So here's the idea, guys. I know I'm going to hit the target. I have to hit the target. So that is my sample space. Does that make sense? Okay, so do we have the ability to find the entire target? The entire target's area would be pi r squared, right? What's the radius for this entire target? Uh, 61, right? So right there is your area for the entire target. Okay? That's my denominator. Would you guys agree with that? Now I got to find my numerator. Now I got to find the area of this red circle. Or this red, I don't say red circle, it's red region. And here's kind of the breakdown of this. Our red region would be kind of this region here, right? Okay. Now, what does that look like to you? A donut, okay. The math word for that is annulus, okay. We got to find the area of that thing. The area of that thing, would you guys agree that if I look at the entire circle and then subtract out the white circle, it would give me that annulus or that donut?
Yeah.
Okay, so let's do that, okay. So this circle here, which this would be the yellow one in here, right? It has a radius of 12.2, okay. So the area of the yellow circle would be pi times 12.2 squared, correct? Now here's where people make a mistake on this question. You just got to pay attention to it. It says the width of each zone is 12.2, meaning that is a zone. Does that make sense? And that width there is 12.2. At least that's the way I'm inferring it or interpreting it, okay? So if I wanted to find that radius, okay, what would that have to be? It'd be 12.2 plus 12.2, right? Okay, so that radius is 24.4. 24.4. So can I find the area of that circle then? Area of, I was going to say overall circle would be pi times 24.4 squared. What do I need to do with those two numbers to get this red region here? Subtract them, okay? So I go 24.4 squared pi minus 12.2 squared pi. That's going to be my numerator. That's the red region. 61 squared pi. That's my denominator. And that's my total target. Now, I'm not going to evaluate it with you right now, but that is what you would do. You type that in your calculator. That's going to give you the probability of hitting the red. Okay? What if I said, what's the probability of not hitting yellow? Probability of not hitting yellow. Do you see that it would be a very similar question? You would have to find, if I said probability of not hitting yellow, you would be first trying to figure out maybe everything that I just shaded in purple, right? Okay. And in the event of finding all that shaded purple stuff, you would take the overall target minus the yellow, right? Okay. And then you would take that number and put it all over the entire target area, which I think is something we can feasibly do. But not hitting yellow, is that the same thing as 1 minus probability of hitting yellow? So you see how that might be easier? Because that only involves it having to find the area of the yellow and not having to find the area of the total minus the yellow. Does that make sense, everybody? Okay. So that complement idea should be an efficiency tool for us at some point in some of our questions. For instance, let's say that I gave you this question. One approach, if I'm interested in what's the probability of hitting the white stuff, okay? Well, the white stuff there doesn't have, those aren't regular shapes, right? Those are irregular objects. So I have to do some work to find out that area, okay? Well, probability of hitting the white would be the probability of not hitting the circles, right? So could I find the probability of hitting the circles and then subtract that from 1 and now give me the probability of hitting the white? Okay. You'll see a question like this and we'll kind of glaze over the overall work here. But look at that square. It's 12 by 12, right? Okay. So that's going to be your denominator, okay, for hitting the target. What would be a radius of those circles? Anything? 3. Good. Okay. Because this distance, and this is the concept you're going to use in one of your homework questions, and I think I put it on a test as well. That distance right there is replicated 4 times total, right? Okay. So I take 12 divided by 4, and that gives me the length of 3. That's something to pay attention to in one of your homework questions. Basically what I do is, I think I give you a question that kind of looks like this, where I give you a rectangle, and I think there's like there might be a circle here in the middle, and then semicircles on the edges, okay? And you're going to use kind of the same principle, okay? Is this okay? All right, probability. Geometrically speaking, numerator is the likely or likelihood of an event, or probability is likelihood of an event occurring. The numerator is your favorable outcome. That's where you want your point to come from. The denominator is the point of all places that can come from. Okay. Assignment in Math Excel. We'll talk about this stuff on Monday and Tuesday again. Probably just focusing mainly on examples. And then Wednesday will be your test over chapter 10.